Before we start the movie, I have a lesson for you. I have just received
Ready?
No, but okay.
Perfect. Hi everybody, welcome. Is the recording working? Okay, yes. This is my first time I'm recorded for workshops. I hope I don't get too shy, but I understand that it's helpful. So, good morning everybody. I understood that there was a bit of a trouble for you to get here, but I'm so happy that you are here. And now you get to enjoy this beautiful weather we have in Geneva. This is the gloomiest day I've ever experienced in Geneva. Honestly, like from our window, usually we'd see mountains and everything. And when I woke up, I couldn't even see the tree that we have in the garden. So it's it's very, very gloomy, but I'm happy you're here. Really? Ah, and this week is so warm. I love cross-country skiing and usually cross-country ski in Jura, but this week it's impossible. All the snow is melting. I'm really sad about it. Okay, well, I'm happy you have snow in Belgium. Okay, so welcome again. So today, as you see, we're going to do the cloud chamber workshop. And I'm not sure, have you been told anything about this? Do you know what to expect from today? Not so much? Okay, that's perfect.
One of my pupils built one
Yeah?
years ago.
Oh, at the school, like by themselves? Cool, okay. So then you know a little bit what to expect. And in fact, we're going to talk about today how you could build your own if you wanted to build one, at your school or with your students. Because it is absolutely possible.
No, but okay.
Okay, so can you introduce yourself?
My name is Willem Peters. I am a science teacher and a mathematics teacher in Belgium.
How you were introduced to the Beamlight for School program?
I saw it, well, actually my wife saw it on Facebook. She forwarded it to me, and within the first 30 seconds of me seeing it, I was already applied.
I am Anke Janssens. I am a teacher in the first and second year of high school. I teach science in Antwerp and also STEM.
How you were introduced to the Beamlight for School program?
It's actually quite a boring story. Jean-Pierre posted something on a Facebook page about this trip, and then that's how I got into this trip, and then I researched him and I learned about Beamline for schools and everything.
I'm Ivo Thiessen. I'm a master science teacher in Belgium for a school in Antwerp at the New Merksem. I teach students of the 4th and 5th, 6th grade, preparing them for university and high school education.
How you were introduced to the Beamlight for School program?
The Beamline for School, frankly speaking, I learned about it when we arrived at CERN. When I heard Jean-Pierre talking about it, that's the first time I really heard about the Beamline school program. Yeah.
Hello, I am Anne Suvé. I teach physics to teenagers of 16, 17, 18-year-olds in a school in Bruges. It was holidays and I saw it pass by on Facebook and I thought I really have to be there, so I wrote a mail to Jean-Pierre.
Hi, my name is Alexandra Moorkens. I'm from a school in Schoten, SBS Zonnebos. It's a special needs education.
Okay. I guess so.
One, two, three. Can you introduce yourself?
Yeah, I'm Kjell Olieslagers. I'm a teacher, techniques, electrotechnics, and science introduction at the school in Arendonk, Belgium.
How you were introduced to the Beam Light for School program?
In August 2024, I saw the word CERN coming up to my computer screen through Facebook. So yeah, that triggered me immediately to react.
Hi, my name is Geertje Strijkers. I'm a teacher from Antwerp, 7 years now.
How you were introduced to the Beam Light for School program?
Actually, through Facebook. I saw it passing by and I thought, wow, this is interesting. So that's why I sent an email to Jean-Pierre.
I am now going to tell you about how we assemble this cloud chamber. You're going to do assembly yourself over there in the experimental area. We're going to observe some very cool physics. And then we're going to finish with like a small presentation by me, but also like a larger discussion between all of us. So I'm going to ask you to keep track of a few things that you observed today. And at the end, we'll get together here and we'll all just discuss what we saw, and maybe we all have the same questions, or maybe you or even have answers to some of these questions. So we have about an hour and a half, so plenty of time. Okay, so what is the cloud chamber? Well, the cloud chamber is a particle detector. So today you will assemble your own particle detector and you will observe particles yourselves. And something which is really cool is that the cloud chamber was actually involved with 2 different Nobel Prizes. So today you will build something yourself that has been part of 2 Nobel Prizes, which is a pretty cool achievement. So the first one over here, we have Charles Wilson, who actually created the first cloud chamber. So he's a Scottish scientist, physicist, who observed some really cool cloud phenomena in like the Scottish mountains. So he wanted to build his own little setup where he could create clouds and try to see these phenomena himself. But as he did it, he realized that he could observe particles with the cloud chamber. So then he kind of switched his research and then decided to be like, okay, let's study particles with this setup instead. And for that, he was awarded a Nobel Prize because this setup, the cloud chamber, had led to other particle discoveries. For example, we have here the discovery of the positron. Are you familiar with antiparticles? Is that something you heard about? Yeah? Do you know like what's the difference between an antiparticle and a normal particle? The charge. Exactly. So in the case of the positron, it's the antiparticle of the electron. So it's exactly the same as the electron, but it has a different charge. Okay, now we get to the assembly part, because really I don't need to stand here and lecture all day. The fun part is for you to build it yourself and start observing positrons and other particles. So I'm going to talk you through how to assemble one, and then it's kind of hands off. You get to do it yourself. If you forget something, you ask one of your peers. Because really I want you to feel like, you know, you should find your inner scientist here today. Like you should really feel like you did this yourself.
So this plastic box is put upside down?
Yeah, so exactly, yeah. Like this, yeah.
Like that, eh?
Exactly, so you get like this kind of like sealed chamber.
Okay.
Exactly, yeah. I can try to remove that one. Perfect.
Without safety gloves, because...
I mean, to be honest, as you noticed right now, the safety gloves, they're kind of tricky to like manipulate things with. So for example, sometimes when we work with liquid nitrogen, which is at like minus 200 degrees Celsius, we don't use the safety gloves because it's easier for accidents, because they're like hard to handle with, yeah. So.
I think you should do gloves as well.
Yes. Very good, very good.
Is one enough if I keep my one hand on the back? I should wear 2, I see.
Maybe 2. So you can ask somebody, maybe if there is, right here, let me give you another one. Okay, you were quick. That's good. So when everybody's finished, we're going to turn off the lights, and that really helps with the observation.
Glow in the dark?
I will be giving you some torches. I will be sharing how it's possible to build your own, so that's the best I can do. Okay, again. Okay. So, I'll be giving you some torches. We'll need them for the next step. Some torches. Okay. Oh, sorry. There you go. 2 torches. I'll explain a bit more in a second. I have 2 torches. I'll explain more in a second about those. There you go. Okay. Okay. So everybody has successfully assembled their chambers, so we can start observing. But to make that easier, we're going to turn off the lights, actually put down the curtains as well to make it really dark in here. And then we're going to use torches. You can still take pictures, you can still use your phones, that's totally okay. In fact, you can get some really cool time lapses. So the way that I would recommend using the torches is if you click the red button until you get to the point where it's like this, and then you place it kind of leaning. Actually, in fact, you can try to see what's the best configuration, but something like this. And you can put the other one as well on the other side. So you put it in streamline mode on the other side. I'm going to turn off the lights and put down the curtains. Love to keep it in place. Yeah, I would say this may be the end, but there is something about the setup that creates the cloud. And in fact, this setup means that the cloud is only at the bottom. So maybe that gives away what is at the bottom, which creates the cloud. Exactly. So there's really a temperature difference. If we had a larger temperature difference, let's say we would heat the top for the particle to turn.
Yeah, because it's a collision. I suppose it's a collision.
Or just if it's...
But I didn't expect
without magnetic field.
Yeah, there is no way to...
So I would suggest, like, one thing is, for example, to draw the different tracks you see. You might have seen like long ones, short ones, questions. The point is kind of to find your inner scientist today. So I'm not here to give all the answers. We're gonna at the end gather where we're at the beginning and try to like chicken like. But this is like just like think about it, brainstorm, and then we discuss it at the end. Perfect.
All over Europe participate. And this is what I wanted to set up a cloud chamber in near space.
Yeah.
And see what happens.
Yeah.
And then I think, so the question that the shaking thing you could try to solve by, I don't know.
Yeah, the keeping it somehow like, yeah,
so
like a stabilizer.
Yeah. Somehow, but then the temperature issue is still problematic. I didn't know about it.
But I mean, like, again, maybe you could solve it somehow. You put it inside of a box that you keep the temperature constant.
Yes, and
but
do that in a glass ball. If you do it in a ball and the ball shifts, doesn't really matter what's up or what's down. As long as, but it will stick to the ice. This now is stuck to the ice, so that.
But so gravity is the thing that pulls down the gas. So if we put it upside down and the cold source up here, the gas will unfortunately fall down as opposed to the cold source.
From the cold source.
Yeah. So that's another thing, as you actually started to notice already now, is that you see like
it will be if you put it in a ball in a loose chamber, it can like sort of shift with it. Whenever the balloon, it's a balloon, huh? When when wind touches it, it goes sideways. But because it's a ball and you put it in some sort of like,
it's a frictionless ball, or no?
Well, you know, like the thing cameramen use to stabilize.
Yeah.
If it always stays on the same.
As long as it stays with the gravity pointing down.
You can think of solutions.
The only thing is that now that you're getting this like liquid forming at the bottom. So with this setup, I mean, that's why this workshop isn't 3 hours long, because it starts to degrade and it doesn't work like in a moment. I think already now the cloud isn't clear anymore. Yeah. So I mean, there is a lot actually when you go.
First, I thought it was full, so Jean-Pierre mailed me that the opportunity was gone because it was already full. And then in August, he sent me an email that I could join, so I was really happy, of course.
I have to go there. It's the mecca of science in Europe or in the world. So yeah, it's a once in a lifetime opportunity. So we just needed to go there.
Oh, it was a dream come true. It's something I have dreamed of since I started studying physics at university. Yes, it was. Yeah, I felt a boy again.
Well, I was very excited and hoping I would get into the program really, and it's amazing so far. So it was a good choice to apply.
What was your first reaction when you heard about visit to CERN?
I was very happy. I was like, I'm jumping up and down, like literally jumping up and down, because never I imagined that I would be here, I would get the chance to visit this. I also immediately sent this to people or told it to my parents or my colleagues, and everyone was like, "Oh, this is so cool!" So yeah.
It is overwhelming. For me, this is the mecca of physics, the mecca of physicists. Even when you don't understand everything what is told, even if you only don't understand 50% from what is told, you still learn a lot, and you keep learning. It's overwhelming. It's I have no words to describe it.
Slices one by one were moved from the main area here with the cranes. They were moved here and then lowered very slow, because this is a one-to-one representation of CMS. So you can see that the shaft is, let's say, exact. Yeah. So the one, obviously, when you lower something, the object can start to make, let's say, some oscillation and so on. So it was a very delicate operation to avoid that the CMS slices went against the walls. And indeed, for the biggest slice, it took like 10 hours to lower it. Yeah, because it was very slow. So, and indeed, let's say the company that made this work also now builds basically stadium because they got a lot of experience to move heavy stuff. And here, so yeah, here you see a representation of the tunnel, and also the experimental cavern on the right. So when we will go underground, we will actually be stay on one of these balcony on the sides of CMS on this side. So here you can see that CMS can be opened slice by slice, and together we should see the main the slice that close CMS, that is called the end cap, and the main part that is called usually the barrel that contains the other slices. 1 week ago there was also possible to see different slices opened, but let's see now today what is the situation. But at least we will see the end cap separated by the rest of CMS and see what is in the middle. And this is very helpful to make operations with CMS, because if you need to fix a part that is in the middle of CMS, you don't need to go inside the experiment, but you can open it and act where you need. So
why is it in shutdown now? Is it preparing for new experiments? Or?
So usually the data taking periods last like 3-4 years. But even when you take data, you shut down the experiments in the LHC for 3 months. So we shut down the LHC and the experiments in November. So December, January, and February, everything is shut down. Both, let's say, to look at the detectors to see if there's something got damaged in the meantime and make some interventions, but also because these experiments requires a lot of current, a lot of energy. And so in the winter, since the energy is taken by the local electric infrastructure, during the winter where people, let's say, relies on the electric power for heating and so on, we prefer to not overload the local infrastructure.
And it's every year?
Yeah.
Every year,
Yeah,
6 months that you
yeah.
close to
Yeah.
just check everything
Yeah.
and
And in the meantime, let people use the heaters in their home, let's say.
So there's no electric power plants.
Of CERN, no. For the moment, we have contracts with the French and Swiss suppliers to get the current, let's say. For now, then in the future, for other experiments, probably we'll need some homemade suppliers. Let's see.
and some slices are going to be the
First time I saw it was in 2020.
Ah, okay, so a bit of time ago.
Yeah. It's the 4th time.
Okay, that's good.
It's impressive.
Okay. Have you seen open it? Have you seen already open?
No.
Ah, okay, the first time. So.
This you mean?
Yeah.
Yeah.
Okay. So today we can see the end cap, that it is the part that closes CMS. Then here we have the parts of the sub-detectors that measure the particles escaping CMS on this direction. And then, then here we have the other slices of CMS for the inner part.
So can you tell us where we are today and why we are here?
We are at CERN at this time being, and we are with the first, let's say, tryout of the Belgian teacher program. So we're here with 22 Belgian teachers, most of them physical teachers. So we're here for him and for them in the paradise, what they call. The main aim of this project is to get youngsters interested in science. And when you want to reach that, it's highly needed that you, the first time, make the teachers enthusiastic. That's the point. Plus, the second, with a bit of luck, we start in 2027 with a real Belgian teacher program, and I'd say that is a first tryout. The participants now, most of them are real physics teachers for high school students, so for students 16, 17, 18 years old. Why it's important to me? Because I like to make people enthusiastic. Youngsters, they are the futures, yeah? And we need good scientists. And to reach that goal, you need very good teachers. And you know, you're here in the place where the Higgs parts is discovered. For a physics teachers, this is the Valhalla. This is the best place to be. And when you bring them here, they are enthusiastic and they learn a lot. And they're in the place where it's all happened.
What is your message to teachers around the world?
Stay learning. So, as a teacher, you're graduate, and okay, you learn a lot of things, but you must stay learning. Must stay learning new things and stay enthusiastic about new discoveries. That's super important.
Voilà.
Dat ik hou van de color coding. Zo. Het geel is altijd uw hangbrug. Maar in de andere gebouwen hadden de buizen, de afsluitingsbuizen, ook specifieke kleuren. Voor,
Ik heb nog nooit bij stilgestaan eigenlijk.
Alright, so we are in the antimatter factory. Now, what is the whole point? So the idea was the following, right? I don't know if you know where antimatter comes from theoretically. It was Dirac who predicted it in the 1930s somewhere. So Dirac was the first one to actually make a theory that combines quantum mechanics with relativity. Why was that important? Well, because particles sometimes move very fast, so they become relativistic. And when they move close to the speed of light, they get relativistic effect. There, you know, time slows down, these kind of things. And the particles, so they're quantum mechanics. The only point was that the only way he could make the theory was to allow for a particle to have negative energy. So in his theory, this is because at some point there's a dependence on the square. So you take the square root, but then it can be positive or negative. And then of course you could say, no, only positive, but that is very unphysical in the sense that if your theory allows the other one, well, either your theory is wrong or the other one exists. Everything else of the theory worked very nicely. So he believed that this is the correct model. It's actually the basis of what we still use today for quantum field theory. And so he didn't like this negative energy. What would it mean, negative energy? And he just moved the sign. If you do -5 times 3, it's the same as 3 times -5. So he moved the sign somewhere else, the charge. And instead of saying, I have one particle that can be positive energy, negative energy, he chose to say, I have one particle with positive energy, antiparticle with positive energy. Why do I stress this? Because it's a choice. There is no difference between particles and antiparticles. It is just another energy state, if you want. And it's a very fundamental thing because we always see as antiparticles as the cancelling particles, you know, the mirror particles. No. It is the same type of particle, different energy state. So why does it matter? Well, if it is the same type of particle, it also means that there is no fundamental difference, right? Matter, antimatter is kind of the same thing. Then why is the whole universe built from matter? There is an asymmetry, apparently, because everything we see, everything we know is made from matter. Okay, we have antimatter in cosmic radiation, but that doesn't count because it's created in the atmosphere, right? So everything we see is matter, not antimatter. Now we can calculate it. We can calculate, based on the cosmic background radiation, what is the amount of matter, antimatter that is generated in the Big Bang, the amount of energy that's generated. And we do that. And if you take one universe as one unit, right? Then at the moment of the Big Bang, we had 10 billion anti-universes and 10 billion plus 1 universes. The 10 billion cancelled out. The one left then is our current universe, right? We don't like that. We don't like asymmetries which are so incredibly subtle. If one would imagine 1 and 2, okay, fine, there is an asymmetric trio. But it's like almost the same. 10 digits behind the comma, it's different. We don't like that. But it also means that, well, there is something we're missing. Because if you create matter, antimatter, as in the Big Bang, you create it from energy, which is, for example, a photon decaying in matter, antimatter pairs. Then there should be as many of them. Then it should be symmetric. The same way, if you analyze, they meet and they become 2 photons again. They don't disappear, they go into energy, so they become 2 photons and they radiate away. Also, that is symmetric. It's not that once you have just a particle and the antiparticle stays or so. Well, that is the logic, but apparently it's not true, because we have one universe out of matter. It would be very boring Big Bang if everything cancels out and everything is gone, right? This is, however, what we expect. So we don't know where the antisymmetry comes from. there is only a few possible explanations, right? Either, well, it's not generated symmetrically. So that means that sometimes a photon fails to generate both and only generates one. It doesn't decay symmetrically. Sometimes, and we're talking 1 in 10 billion times, because that's the change we're looking at. One of them survives in a decay. These are very improbable, by the way, because it violates a lot of fundamental laws that we believe are holding. Another possible solution is that antimatter is inherently more unstable. It's also very unlikely because, well, it should be the same kind of thing, right? Another possible explanation is that, but there is all the antimatter. It's somewhere else in the universe. I mean, you could imagine, we only see 20% of the universe, observable universe, could be behind it. Well, I mean, sure, but why did it then generate? I mean, it generates locally, both of them, right? Why do then, and all the antiparticles go on one side and all the particles on the other side? All of these have problems. We don't know. So what we do know is that, well, let's look at them, right? Let's start making antimatter. And that was actually one of the first goals of the antimatter facility. It's the AD antimatter decelerator. We'll come to that in a bit, why it's a decelerator. Now, the idea is the following. If it's the same, everything could have been built from antimatter as well. We would have called it matter, right? I mean, no difference. So then you would have had anti-wooden pallets, anti-floor, anti-chair, whatever. What do you need to be able to make things? Well, you need elements, molecules, etc. But lower level, you need elements. The Mendeleev table. The only thing we have in antimatter is, well, antiparticles, not anti-atoms, right? So can we make anti-atoms? The easy one is anti-hydrogen, because anti-helium, we need to start adding fusion. We do not manage fusion with normal particles, let alone with antiparticles. So let's focus on anti-hydrogen, right? And then the idea is the following. Imagine we make anti-hydrogen, let's study it and compare it to hydrogen. Magnetic moment of the atom, of the nucleus, the spectral lines when you excite the anti-hydrogen and all these things. Are there differences? We don't expect to see differences, right? But there should somewhere be a difference. Let's see if we can find it there. It's not that trivial. First of all, you need antiprotons, right? Anti-electrons are easy. They're beta plus radiation, positrons, so they occur naturally. Okay, you need a big flux and blah, 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 but it exists. Antiprotons you need to make. We have made them since the 60s or so this is possible, but we never made them steered. It's not that trivial. I will come back to that. Then, well, it's not because you have both ingredients that they are an atom. By the way, I don't know your background. You're physics teachers?
Science teachers.
Science teachers? Yeah. Very good. Okay, so then I can go in this kind of detail. So we always see as the atom as a nucleus with electrons around it, or in orbits, if you want to be more precise, probability functions, etc. But even that is quite wrong in the sense that these are the constituents. You only see them when you break it open. An atom is a neutral particle. It's bound. And we are so used of thinking of its constituents that we forget the fact that as long as it is bound, it is one particle, not fundamental. It is one particle. It does not behave following its constituents. It behaves as one neutral particle, right? It's very easy to unbind it because the binding energy is very low. You don't need a very strong electric field to ionize it, so to unbind it. And because it's so easy, we always think, but it is the electrons stripped off. No, before it was one particle. It's a detail, but it's an important one. Same with protons, for example. Protons have 3 quarks. No, proton is a proton. It's a not a fundamental, but a bound particle. It's a composite particle. As long as you don't break it open, you see it as one particle. Protons are very weird, actually, because they will get more than 3 quarks, because they will have a bunch of gluons, quark, antiquark pairs, etc. The moment you break it open, depends on what moment you break it open, you'll see a bunch of quarks coming out. So, even then, people think like, how do they all fit? Irrelevant. Before you broke it open, it was one particle. It's a mind shift a bit. We're too used to the constituents. Why do I stress it? Well, because going from antiproton and positron to antihydrogen is this binding step. And the binding will be broken the moment you have an energy in the system that is higher than the binding energy. You don't need an electric field. If you would take hydrogen and you move it so that the kinetic energy is higher than the binding, it will fall apart. The opposite is true. You will not bind an antiproton and a positron when the kinetic energy is higher than the binding energy. This binding energy is so low that you need to cool down your antiprotons enormously before they will bind, which is why we have a decelerator.
Nee, maar en de opnames
en de opname moet ik tegen het
kan er zo, want hij komt achter u aan als je te laat bent.
Ik was 3 minuten te laat.
Zijn we hierna maar één groep dan, of wat?
Dat zijn er 10, dus misschien kunt je die in één groep pakken.
Ja, jullie konden ook in één groep pakken. Dat is een beetje stom. Hallo.
Without any question, that was the visit of the Antimatter factory, where they produce antimatter, the only place in the whole world where they do that. And also the fact that one doesn't know yet where all the antimatter has gone. The moments after the Big Bang, that's a very interesting study.
It was an incredible experience, first of all. Meeting people you won't probably meet in your life normally, and seeing things you won't probably see normally. It's too much to name them all, but an underground visit to CMS and an antimatter factory is not something you can see in daily life. So it's yeah, once in a lifetime.
It's been very good until now. We've met very interesting people, and the sheer view of all these material, all the detectors, it is so huge that it's very impressive.
Okay. So, well, my name is Markus Joos. Like most of the colleagues that are going to meet at CERN, I'm not a physicist. I'm an engineer. And you are, well, going to find out that there are very, very few physicists employed by CERN. Because CERN is an infrastructure organization, our job is to build accelerators and to operate them. And all the physicists that you would meet here, they are actually not on our payroll. They are what we call users. There are about 13,000 of them registered. Usually they are not here, they are at their home universities, they teach their students, they analyze data, but once, twice a year they come for a shorter or longer stay to work on their respective experiments. Well, I came to CERN in 1993. They asked me to become a specialist for a certain type of electronics modules, electronics that we are using in the readout system of the Atlas experiment. So for the first 20 years of my career, I mainly did software development. And then I moved more into education and outreach. Beamline for Schools is probably my biggest project. But I also organize some schools where me and my colleagues teach young scientists how to build big data acquisition systems. And in a moment I'm going to well, give you my take on computing at CERN. But to introduce it and to make it a bit more fun, I have a quiz. Well, everybody is allowed to participate except for those who have already participated once. So, sorry, Jean-Pierre. The quiz is very, of course, yes. It's very simple, 13 questions, multiple choice. For each correct answer you get 1 point. So in the end your result should be an integer between 0 and 13, just for a sanity check. And of course there is a prize to win. And of course I have full confidence in you. So just, well, mentally sum up your score, and we see in the end who is going to win the prize. You can also take paper and pencil if you want. Yeah. Okay, ready to go? Question number 1. Who has got the least computing power? CERN, Amazon, or Facebook? So, but just decide for yourself.
Is it Facebook or is it Meta?
Doesn't matter. Okay, all made your choice? So here comes the correct answer. Who got this right? Okay, so you now have 1 point. Simple. How much data can be sent through an optical fiber? 1, 100 or 10,000 DVDs per second. In case you don't remember what a DVD was, it's an optical storage media with a capacity of 5 gigabyte. Okay, so make your choice. How large is the daily worldwide internet traffic? 8 times 10 to the 15, 18 or 21 bytes? It is. To put that into perspective, it's 1 gigabyte per person and day. So a gigabyte, that's about or maybe half an hour of video streaming. Number 4. Dropbox, and I'm not making any publicity for this company, is offering 2 terabyte of storage, space cloud storage, for 120 euros per year. How much would 2 terabyte of storage capacity cost if you buy a hard disk yourself? 60, 120, 240 euros. Good remark. I do update the slides every now and then. But you can scale it a little bit, yes.
Because I pay that.
Well, in that case, the correct answer should not be too difficult. It is 60 euros. What would have been the cost in 1960 for storing a Twitter message? 280 characters. 4, 40 or 400 US dollars? Okay, it is. Mm-hmm. How many transistors are in a modern computer processor? 100 million, 100 billion, 100 trillion? Well, I like these questions because between each of the answers there are 3 orders of magnitude. And you still don't know what's correct. Well, and correct answer is? How many transistors are produced worldwide per second? 6 times 10 to the 7, 10 to the 10, or 10 to the 13? Okay, make your choice. So, for a change, biology. How many neurons are in a human brain? 880 or 800 billion? So it is 80 billion neurons in a brain. Let's have a break. You don't have to calculate, don't worry, I do it for you. What we have learned so far is that every second there are 6 times 10 to the 13 new transistors. There are 68,400 seconds per day, 8 times 10 to the 10 neurons per brain, and Google tells us that every day there are 360,000 babies born. And now we can multiply. And the result is that per day there are 5 times 10 to the 18 new transistors and 3 times 10 to the 16 new neurons. So you probably understand where all this AI hype is coming from. Well, the neuron production is sort of flat, well, with a little growth rate, but transistor production is still exponential. And you see, for every new neuron, there are already 100 new transistors. And if you just scale this up for another 5, 10, 20 years, well, we live in interesting times. That's for sure. Well, we know that high school students typically don't understand all the details of particle physics yet. They need somebody who guides them through this experience. And high school teachers are, of course, the first contacts that they can ask when they have specific questions. But they can also go a step further and, for example, contact a physicist at a university who would also be able to help them.
What would be your main message to the teachers and students around the world?
Well, my main message to both of them is take the challenge. No matter how well you do in this competition, you are in any case learning something new. You can go a bit out of your comfort zone. You can take a challenge. And I know from many of the participants that they found this very, very enriching. In June 2021, Sotheby auctioned an NFT. You know what an NFT is? Okay. For the original source code that was used to build the World Wide Web. What was the price? So how much did somebody pay to call himself? Super, thanks very much. So how much did somebody pay for calling himself the owner of code that is in the public domain? Yes. No. Well, one of you has to go first, and then the other one has to decide more or less. $1 million, okay.
1.8 million.
Okay, we have a winner. Your prize is this. Well, not the paper. When you unpack it, you will find a computer CPU inside. This CPU is, well, roughly 20 years old. We bought it in the late 2000s. It was installed in the data acquisition system of the Atlas experiment at the time that we discovered the Higgs particle. So this is a Nobel Prize winning CPU.
Very cool.
Wow.
All with a lot of guessing too.
How do you think a visit to CERN will impact your further teaching?
A few things, really. There's a few. I get to be more motivated to teach my subjects because I saw new things. I want to explain them to my family or my pupils, and motivation is key when you're teaching. So mostly that. Also, like you have the group sessions with the workshops, which were very interesting and really hands-on for students. So I'm gonna make my own, or the students are gonna make their own cloud chamber like later this semester.
Well, first of all, it's very motivating seeing people here who had a technical education, scientific education. So that's what we teach to the children, and also we had some very useful tips of doing stuff in class, what they did here, so we can transfer it directly to our own education things.
Is the thing is on? Maybe check. Good. Okay. Okay. So it seems like your schedule is very busy. So then you're happy to hear that today's workshop is going to be a little bit more relaxed, less challenging than yesterday. So we have these 2 workshop rooms. So you were in the other one yesterday, and over there we have workshops which are aimed towards older kids or an older audience. So for example, the students are usually from the age of 16 to 19, or the general public, but we have like an age limit of like 12 for most of the workshops over there. On this side, in this lab, our workshops are aimed towards younger audiences. So here is from like the age of 3 until 16. Okay, so there are 3 experimental phases. The first one is to explore different type of air pads. So as you can imagine, the airflow is important. Depending on the airflow, you can lift objects with different types of weight. So we have a few different air pads and you have a few different surfaces. One of them is, for example, like a floor mat. So maybe you will discover that the best surface is a floor mat, so we should put the floor mat in the CMS cavern perhaps. But you get to explore different types of surfaces and different type of air pads like this. In the second one, we have a bunch of Lego bricks. We love to use Lego bricks because they're so easy for the kids to use. And you get to try and build something out of the Lego bricks. So try and make like the heaviest thing you can lift with the air pads. So this is you to be a bit creative and explore. And then the final one, we actually have 3D printed CMS detectors. And you get to kind of to construct something which you can use your own 2 air pads to move part of the end cap to the rest of the CMS detector. And here at CERN, we need some way to blow up the balloons. But of course, because we're at CERN, we like to make everything very complicated and use very, very fancy tools. So instead of blowing it up with your mouth, we have these very expensive tools that blow out air. So to blow up the balloons, you can just add them like this. Be a bit careful actually not to rip it, but of course if it happens, I'll give you another one. You pull this towards yourself and then you rotate it. And you try to get a balloon as big as possible. Then you get it off, and my recommendation is that you twist it, because now you need to attach it to the air pad, which everybody will have at the table. And this is like slightly challenging unless you twist it. So you attach it, then you untwist it, and now you have an air pad. So you will have different types of airflow. So you get to explore which type of airflow is the best one to kind of create your own little hovercraft, and also the size of the balloon. But yeah, so this is the basics of today's workshop. And you have everything here in the trays, you have all the instructions. So I think you can just split about 4 people at the table. Actually, you might have to be a few more this time because one of the fly ones aren't working. But yeah.
Well, all of our civilization is based on scientific results. So if we want to keep the level of technology that we have at the moment, but if we want to do this, for example, in a way that's less harmful to the environment, we have to improve our understanding of science in order to be more innovative in the future.
I think first of all we can do a lot with it. For example, medicine and all those things are all science, and then I think it's just understanding who we are, how we got here, everything around us, and I think it's very important to know all those things before you go on with your life.
Yeah, actually sit on it.
Stand on the plate, turn on the leaf blower, and
Yeah. Okay. Anybody else?
So you said?
Yeah, so if you hold, exactly, if you hold that one, as long as you hold it, you will, yeah, it will work. If you just hold, if you do this one all the way over here, that like then it goes the
Then you can try the moment stuff. You know?
Oh!
Yeah! You want to try?
Yeah, I want to try it, yeah. Actually,
yeah.
So not trying to set home should
I
be
feel
here.
like I need to close the curtains because we told the kids to sit down. In case somebody of my supervisor team
How many questions do you have? 120?
Just 3. No.
No.
Just very brief. So, how are you feeling today?
Tired. It was a very busy week with a lot of troubles, but okay, everything is solved.
What time is it now?
No idea. I guess about 8.
Yeah. It's 8
Okay.
in the morning.
Wow, 8 in the morning. But I left at 5.
Yeah. How challenging this time was the organization of visit to CERN?
Very.
This visit?
Very, because it's not visit as usual. So a visit is Science Gateway, 2 visits, maybe 1 lecture. That's it. But thanks to Brussels Airlines, we extended our journey, our stay at CERN. So extra lectures, extra events. It was very stressful to organize this all, but it was really something amazing.
The days are tight scheduled and we did a lot of walking in between and running most of the times. And where do you get energy?
Don't know. That's just me. So I have a lot of energy. I'm tired, okay, but it's still, everything is still running fine. My brains are still working, so okay. The adrenaline is still flowing.
Any message to the visiting teachers?
stay enthusiastic. So you were here at CERN, you have got a lot of lectures, 8 if I get it right. You have seen a lot of research facilities. I saw you all very enthusiastic, very big smile. So I always say my goal is to make young people enthusiastic, and to reach that I need enthusiastic teachers. And these are the words of Fabiola Gianotti yesterday. Please go on, we need enthusiastic young people, and therefore we must educate the teachers.
The thing is that next you're going to be in the exhibitions. And the walk around. So would anyone want to try before you go? Okay.
Can you make it move just by stepping aside? Or
yeah, no,
can you decide?
So we usually don't do it. We always the kids sit down, hold on tight, you know. We have a little try.
One, two, three. Any essential message to Jean-Pierre?
Yeah, thanks a lot, Jean-Pierre.
Thank you for organizing this. This has been a unique experience. I don't think there will be anything in the future for me that's as special as this. I hope his project with SSVI will continue, and that he is able to find the motivation to do everything he does, because he's a special person. He did amazing things this weekend.
I really want to thank him for this experience, because I think it's a once in a lifetime, and I really enjoy it. So thank you very much, Jean-Pierre. I just really want to thank him, and maybe I'll hope to see him again somewhere, somehow, because this was really for me an exceptional opportunity to come here. So thank you, Jean-Pierre.
Thank you so much, Jean-Pierre. It's been so great. Thank you for all this organization.
Thank you, Jean-Pierre, and let's do it again.
Thank you,
Jean-Pierre.
Thank you, Jean-Pierre.
Thank you.
Thank you very much.
Thank you for everything.
Yeah. See you soon, hopefully. Bye-bye.
Your teacher? And they said none. They heard about the competition. They spent their lunch breaks at school to talk about different ideas. And in the end they came to a point where they realized that they need expert help. Their teacher was not available for whatever reason, so they contacted the professor at the university. And that's also a pattern that we see very often. Students start to contact universities, and we are lowering the bar a little bit.
So there is an outreach proposal. Yeah? I have put on the page this afternoon a big block, Beamline for Schools, with a link of the website. And in that link, we go to the outreach proposal prize. You can see what you can win. And this year is really very exceptional. I can't do that every year. I can't visit every year. Markus told me, okay, Nobel Prize wins. I'm used to it. But if you can get